So today we're going to talk about, again, we will talk about the way we solve equations, but this time we will look at this from a little bit different angle. We'll look at this from the angle of factorizing polynomials, and you will see that actually solving equations for roots, it's actually the key step in factorizing polynomials. So first I'll recall for you the fundamental theorem of algebra. I mentioned this before. I'll say it again to you, and I'll recall it for you again. So generally, if you look at the polynomial, p of x, any polynomial can be written like so. You have some a0 coefficient xn, a1 x, and take 1 plus, you can go all the way down to the coefficient an. And that's how generally every polynomial looks. Now for such polynomial, n here, of course, it's the integer, bigger than 1. For such polynomial, of course, you think of the coefficients here as in complex numbers now. All the time we deal with the polynomials, we think of complex numbers. And if you set additionally that your highest coefficient, a0, is non-zero, generally it might be 0, then it will be a smaller polynomial. But if it is non-zero, then you say, it's just a bit of a terminology for you, you say that the degree of this polynomial is n. Now, that's the setup of the fundamental theorem of algebra, and the actual claim of the theorem, it says that, here somewhere, I'll say this is a claim number 1, it says that for such a polynomial, you can always find, remember this symbol, this is the one which reads exists, you can always find a number, z0, which is a complex in general, and that's the number which vanishes your polynomial. So that's a number which, if you plug it in, it will give you 0. The theorem, it's a fundamental result. The discovery of this result was a big success. However, from your perspective, this is not really something of great interest. You won't find this of great interest because the theorem itself doesn't give you the method how to find this solution. You can sort of restate this result like so, and that's something I call part 1a. This existence of the root, it also implies that you can factorize your polynomial like so. So you can just find this linear bracket. You can find this actually another polynomial, q, and the degree of that polynomial will be by 1 less, so it will be n take 1. This new polynomial will be connected with the original one by this identity, and that's what we call the factorization of this single root, the existence of which is ensured by the fundamental theorem of algebra. This one actually is a practical step. We know how to do that. We'll do this kind of step today a few times, in fact. But I showed you how to do it before too. If you know the root, how to factor out the corresponding linear bracket. In fact, we can actually extend this result. We can actually extend the statement of the fundamental theorem of algebra even further. Instead of saying that there's only one root, we can say, in fact, because if it's one root, then we can look at this new polynomial q, and then we can expand that, we can actually find the root in this polynomial too, again, referring back to fundamental theorem of the algebra. If you do this referral to the fundamental theorem of algebra n times in a row, in fact, you will be able to find the whole bunch of roots from 1 to n, not just one, but the whole n roots, where n is the degree of your polynomial. Each of those roots, if you plug them into your polynomial, all of them will be equal 0. So in fact, the advanced version of the fundamental theorem of the algebra, fundamental theorem of the algebra, it says actually for the polynomial of degree n, as long as n bigger than 1, bigger or equal than 1, you can find n different solutions. And you can also factorize your polynomial in n, with the n linear factor. So the complete factorization will look like this. The highest coefficient, a0, which we remember, we assume this coefficient on 0, by the way. And then you factor out all of the linear brackets with all of the roots present in them. So in fact, in principle, we don't have like a universal tool how to do that. But in principle, you might expect that every polynomial factors like so. Yeah, I was planning to give a bit of a comment about this in principle, which I added. Like I said, in general, for any algebraic equation, there is no method how to find the root. However, if the degree is less than 4, I'll say it here. No, I just say degree polynomial less than 4. For this special case of the polynomials like linear polynomials, quadratics, cubics, and I'm not sure if there's a word for four. Huh? Quartics. Quartics. Actually, there is a method which solves every possible quadratics, cubics, and quartics. For quadratics, you have a formula. I mentioned those. For cubics, you got the Cardano method. We practiced that quite extensively. For quartics, there is also the method. It's named after an Italian fellow. Italians were very strong at that age when these things get developed. His name is Ferrari. I don't think he has relatives with the car making industry, but yeah, still, it's like a car, yes. I think there is a Wikipedia page on that method. If you're curious, you can have a look at that method. It's interesting. However, if degree of your polynomial bigger than 5, people struggle a lot trying to produce a general formula for instance, for the polynomial of 5th degree. For the 5th, actually, I know the word, quintic, it's called. I forgot for the 4th one. Yeah, they struggled a lot, and it was another big success, in fact. It was the success of the German mathematician, and these days we know it as the Abel theorem. Abel's theorem. It says actually that not every polynomial of degree 5 or higher can possibly be solved, can possibly be supplied with the formula for the roots. That's all I can say to you. It's a very difficult result, and it's very difficult to comprehend because we're just sort of expecting that everything might be solvable. At least like in principle, you can find a very huge formula like on 10 pages or something, but still you might think there must be something. Unfortunately, or fortunately, his result very strongly supports proves the idea that no, you can't produce a polynomials of degree 5 for which there is no formula whatsoever. In fact, if you want to do some further reading on the subject, you should also know about this name of this fellow, Évariste Galois. It's a French mathematician with a very sad life story. In fact, he died young. If you Google his name, you will see his young picture, as opposed to many other mathematicians. If you Google their names, you will see their pictures when they're like in 50s or 60s with a beard and everything. Whereas his picture, the only picture which exists is a young one, and actually I think it's a sketchy, it's a picture, not like a photo. He has very sad story. But you can read this. Wikipedia has lots of information about that. But actually, it was his genius. I don't know how he found this because it was 17th century or something. Actually, he was able, though he was in prison for a very long time for his political views and something, but he was able still. He was able to find very revolutionary way to look at the equations, and it's still very modern way. And some of you who continue the study of math in this uni probably will study his theory, Galois. His name, his French name. I think you're supposed to read it, Galois, Évariste Galois. It's very advanced theory. I'll tell you honestly, I don't know all of it myself, but it's like the way how he saw this back in those times when people were, and how he saw this is just amazing, and how he saw this way of looking at the equations, and he gave us a tool, like this result, Abel's theorem. It says us not every equation of degree 5 or higher is solvable, but this fellow actually developed a tool which allows to test every equation whether it is solvable or not. So he